I'll talk about designing geo-distributed cloud infrastructures. And as we all know, most commercial clouds, at least the larger ones today, are already geo-distributed. What in the past might have been a big endeavor for an online service developer to deploy a service in many, many places. Today, it's just like on Windows Azure, for instance, it's just one checkbox on your storage account. When you check that, your storage gets geo-replicated. The questions we want to get into, or the main question we want to get into are, what are the capacity implications? And before we look at that, we need to understand why we are geo-distributing our data centers. First reason is, of course, low latency. Everyone understands that if I'm closer to my customer, my round-trip latencies can be much smaller than if I'm in just one location and trying to cover the whole world. The other reason is high availability. One data center can fail, and hence I want other data centers to be present to pick up the slack. Now, there are, of course, ways to make the single data center very reliable by having power backups and so on. But the reality is that not all failures occur due to well-understood failure models like power. Some of these failures occur due to software bugs. And if you just search for the blogs published by the cloud operators, and many of them are pretty good at actually publishing the reasons of why their data center failed or a large chunk of the data center fails. I'm just pulling up a few of those blog entries. The Azure cloud, for instance, failed because of a bug in the Fabric controller. The Fabric controller is the operations management layer in the cloud infrastructure for Azure. Google had a big failure for a data center, and the reason it turned out was that the operators looked at the wrong documentation. They couldn't find the right document in the case of the failure. Amazon, again, had a similar failure due to a software bug. You can't really prevent these with, say, backups within the single location. And very recently, this is not on the slide, I was just talking with the Azure folks. They had a failure where an entire data center, which had nothing going wrong, power was up, all the software was operating as normal, but it stopped getting any traffic because some ISP misconfigured their router. This is an ISP not part of the Azure cloud infrastructure, something external. They misconfigured their router that made it look like the IP address range of this particular data center is no longer available. So a large chunk of the traffic that was supposed to go to that data center was never reaching it, even though this data center was perfectly fine. So bottom line, you need redundancy at the geo-distributed scale. You need multiple data centers to make up for such failures. And the question we want to address is, how much extra capacity do you need in your system if you want to account for failing data centers? And to that end, let's work with this model. Let's say we have demand coming from a bunch of clients. This map shows the population density in the US. Bluer the region, the more densely populated it is. And as that would suggest, demand in a denser region would be higher. The other point to notice is that across the world, I'm only showing one country here, the time zones do vary. Even within the US, there's a 3-hour difference, which means the peak demand from one time zone is not aligned with the peak demand of the other time zone. So even if I don't put any spare capacity in my data centers, when one data center is peaking, the other data center probably has some idle capacity. So working with this model, let's try to compute what are the capacity implications. Just for example, let's say we only wanted to do multiple data centers to make our system lower latency. We just wanted to be closer to the clients, forget failures. Then compared to a single data center, where I would have the maximum statistical multiplexing advantage because I'll only be serving the sum of the peak demands. Let's say I represent that as capacity 1. Then if I go closer to the clients, and now each of my data centers that's close to the client locations has to meet the local peaks in demand, I end up wasting about 20% capacity. And not necessarily wasting because I'm getting latency benefits, but that's the cost I have to pay. And the other graph shows how much idle capacity exists in the system at different times of day. So that excess capacity is needed really for the peak or a percentile of the peak. You could provision for the 99th percentile instead of 100. You'll still have that excess capacity. The other reason is availability. If I were to pretend that all the data centers are the same sized, then this is a simple calculation that, hey, if I have 6 data centers, then I need 20% extra capacity so that if one of them disappears, the others will have sufficient slack to work, to take up the load. But in reality, of course, data centers are not the same size, or rather they should not be the same size because different regions have different amounts of client demand. And obviously then the question is, what is the optimal capacity that I should provision to meet my latency and availability requirements, where we assume that a failure can happen at any time. It could happen at the time when the demand is peaking. So I'll show one way to calculate that capacity. And for the time being, I'll assume that state replication is already taken care. There's a bunch of work on geo-distributed storage. And let's pretend one of those mechanisms is in place. So yeah, here's how we'll calculate this. Let's say there's a constraint on the latency that I want to achieve. We could take this constraint to be the latency that any of my clients achieve in the approach that I would map every client to the nearest data center. Let's say I have 6 data centers and I map every client gets routed to whichever data center is the nearest. I measure what the latency in that case is. Let's say I take that as my latency constraint. I could take a percentile of that, say the 99th percentile of that, or whichever percentile I want to. So that's a latency constraint when nothing has failed. And let's say we have a second latency constraint after failure. Could be the same, could be slightly more relaxed. And an important assumption I'm making in this calculation is that the service time is the same at every data center. So I'm only worrying about the network latency, not the actual compute latency, which is a reasonable assumption because we can pretend the servers are the same at every data center. The only thing this limits us from doing is ignoring queuing effects. If I were to provision smaller capacity and allow for more queuing, I could achieve or I could serve more client demand with a smaller data center, but we are not worrying about that trade-off here. And then really what we are trying to optimize is the total capacity. Let's say the capacity of the jth data center is Cj. We want to optimize the sum of that. And to formulate the optimization, we need to introduce some variables that denote how much client traffic from each location is going to which data center. That's what the optimization will calculate, how the traffic should be allocated. And the Fijk is the variable for that. And here's the optimization. So if you don't want to worry too much about the equations, what we are doing here is we are minimizing the sum of the data center capacities subject to 2 key constraints. The first constraint is that both before a failure and after a failure, the demand from all clients is served by some data center within the latency bound. And the second constraint is that the capacity of each data center is sufficient to meet the demand it is assigned to serve at any point in time, including the peak time and off-peak times. So if we take that problem and just run it through some standard optimizer, we'll get what the optimal capacity is. And let's look at the results. So this is, I assume that the data center locations are are at the same places where Microsoft has 6 of its data centers. And the paper has results also if you assume 6 of the public locations of, say, Google and Amazon. So to begin with, let's look at the 2 bars that are called out with the red marking. The lower bar there is how much capacity we need when we map every client to the nearest data center, not accounting for any failure. That's 120%. 100% here denotes what we would have if we didn't go geo-distributed at all. This bar one up from that represents the result of the optimization, and it's also about 120%, which is basically saying that, hey, you needed 20% extra capacity to get the lower latency that you wanted. And with that same latency constraint, if you allocate capacity according to how the optimizer computes, you are getting failure tolerance for free. You're getting high availability for no extra capacity. So that's sort of the first point that comes out of this measurement. The other bar, the longest bar on the graph, is showing how much capacity you would have spent had you not taken into account the time of day variations or the time zone differences between data centers. And it turns out then you'd have spent 48% extra capacity as opposed to 20%. That's just for, like, I don't see any reason why one would want to do that, but that's a good number just for reference. I'll come to the other bars in just a minute. So the caveat here is when I map every client to the nearest data center, I get a certain maximum latency for the clients. But if I look at the distribution of the latencies, some clients which are pretty close to the data center are getting very low latency. In the optimization that we formulated, we are setting a limit on latency. So of course, the worst case latency or the 99th percentile latency is the same, but the clients who were earlier getting allocated to some data center very close by might be allocated elsewhere within the latency constraint, but still the latency distribution will change. Let me just show the latency distributions to make that clear. So, okay, this is before that. This is just showing naively allocating capacity. That's the blue bars, mapping the capacity to the nearest data center. That's the size of the capacity needed. The orange bars show what we would need if we did the optimization. Main point being that Virginia, which in this case happens to be very nicely located near densely populated areas, would be trimmed down to smaller capacity, and other places would get more. So yeah, coming back to the latency point. So the orange curve here shows the distribution, the cumulative distribution, if I map every client to the nearest data center. And the blue curve shows the latency distribution when I use my optimizer. So we can make a certain percentile of the latency the same, but the clients who were very close to data centers may get higher latency. As you can see, the blue curve is shifted right as opposed to the orange curve. So there's a slight penalty on latency. Question one can ask is, if I want to keep the same latencies, what would I end up spending? So the gray curve here shows what I would get if I don't want to tolerate failures, but instead of allocating every client to the nearest data center, I do it according to the same optimizer, but without provisioning any extra capacity to account for failure. So the gray curve and the blue curve are pretty close by. So essentially that's saying if we compare the results of those two optimizations, we are looking at how much capacity I need to account for a failure. And that's the top bar I had in the graph. The top bar is showing how much capacity I would need if I allocated capacity according to the optimization. Turns out I need even lesser capacity than the single data center case, because I'm able to use off-peak times from one data center to compensate for peak times at other locations. And overall, compared to that as my baseline, when I do account for a failure, I'm spending about 34% extra. So that's the cost of accounting for failures, just comparing for the same latency distribution. So the point of these calculations is that it is not necessarily trivial to simply allocate a certain percentage extra capacity in every data center. How much extra capacity you give to each individual piece can depend on the demand distributions and time of day effects. Another variation, this is not in the paper, but one can ask the question that, hey, before failure, I just want to map everything to the nearest data center. I don't want any hit on latency. But after a failure, I'm okay to tolerate some latency hit. And after failure, I'll pretend I do the same thing as I was doing before with the optimization, that there's a latency constraint. But before failure, we do what's the lowest latency any allocation can achieve. This graph shows what happens. The blue parts of the bars are the capacities I provision just to serve demand before any failure. The orange parts are required to account for the failure. And remember, these orange bars are sufficient to account for any data center failing, not just like the one, not a particular one. So one thing that's pretty interesting to note here is the largest data center does not have any spare capacity. There's no point putting spare at that data center, because if that data center fails, we'll lose not just the biggest resource that we have, but also our spare. So all the spare is in other locations. And that helps keep the total amount of spare smaller than say provisioning just some set percentage at every data center. So yeah, that's showing how I would want to optimize capacity. Next question one would ask is, let's say the data center or the cloud infrastructure did provision capacity according to that optimization. What's the implication on my software design? If I'm writing an app for the cloud, how will it impact me? First thing is routing. Today, requests are routed using, say, IP Anycast or other mechanisms to the nearest data center. I go to, say, x.com, the DNS servers or whoever figures out this is the nearest data center to serve x.com for me. That won't be the case anymore. In this case, let's say we take Pennsylvania clients. At some time of day, they are allocated to Iowa. At other times of the day, they are allocated to Virginia. So one needs to design the load balancer accordingly. Second implication is, where do I replicate state? Now the capacity allocation optimizer is deciding where spare capacity exists, and that is where the clients will be routed to after a failure, assuming we get the first design right. Then the state data must also exist at those same locations. We could either replicate upfront at the right locations, or we could always replicate nearby, but move the data to the right locations after the real failure happens. Yeah, the paper goes into a little more detail of how one could go about doing that. A third thing that the software will have to look at is the cloud API. Today, clients, just like a tenant who wants to run an app in the cloud, simply request, hey, I need this many VMs. And the cloud will give you that many VMs. There's no guarantee. The cloud could come back and say, hey, I don't have any more VMs to give you. But usually, they would have it, and the tenant would get it. That doesn't really work if the capacity is allocated optimally. If the infrastructure has reserved VMs for you at certain locations, and then it can provide a guarantee that these will be available even if my data center fails, then somehow the tenant needs to know where these VMs are so they can replicate state for their app accordingly. They can potentially pay for these VMs up front so that they are reserved for them. And I think the right API is still something that needs to be figured out for that. So in the interest of time, I'll skip the related works. The paper has all of them. And the key things we are trying to get with this initial phase of our work is that how geo-distribution affects capacity planning and what the implications on software design are. I'm very happy to hear any feedback folks have on guiding future directions on this. Thanks.
Promise not to yell at you this time. Have you considered a distribution of clients with multiple classes of latency requirement? So trying to serve, say, two types of content, for example, where there might be a tight latency and a loose latency requirement, and how that would change your model?
That would simply change some of the constraints in the optimization. We'll potentially provision for 2 units of capacity, one that meets one set of constraints, the other that meets the other set. And the maximum we will take is that the overlap of them should be sufficient at each data center. I'm pretty sure it can be handled. I don't know offhand like whether it will still remain a linear problem or not.
Yeah, I was just curious if you thought about that. Okay, thank you.
Yeah, we haven't done that yet. Yeah.
Hey. Hello. Oh, the question is more about like how this can be used in terms of capacity planning, like as people buy hardware. Is this intended to be a way before you buy the hardware or after you buy the disks and maybe you want to send some of them to a different data center? Is that the intent?
So there are two parts to capacity planning. One part is what I was talking about, which is how much capacity I need in which places, and what's the amount of extra I need in every place. The other part is how will my demand grow over time. So we are not addressing predicting, let's say today I need 100,000 servers to serve all my cloud tenants, and maybe in a couple of years I'll need 200,000 servers. That part needs to come from elsewhere. We're saying that let's say your capacity is 200,000 servers, how should it be distributed among your data centers? That's the part we're trying to solve here.
Okay, but the hardware is bought already, right? Microsoft would have already bought hardware for all these data centers. How do you, so that is a sunk cost.
So often a data center, the location at which it is built, the land is bought up front for a much larger facility because land is super cheap. And power is provisioned for a larger facility than instantiated at any given time. And then servers are populated depending on how much demand we have in, say, right now or in the next certain number of months, whatever the cloud provider decides to provision for. And then this is helping you address how much, let's say I decide to serve 1 unit of demand, which could be 500,000 servers, 100,000 servers, whatever. What percentage extra should I provision to account for failures?
All right, thank you.
Sure.
Any more questions? I guess I'll ask a question. So if I understand in your model, you're thinking a scenario in which a client has some cloud resources and you will be the only one operating on these resources. Is that correct? So what I'm trying to say, asking is, suppose that I'm running a service like Facebook. So effectively, when I do some local updates of my wall, this needs to be reflected in potentially wide range of different data centers, because different other devices in my plant will access from different locations.
Right.
So I was wondering, if the cost of this, consistency, not just replication, but the consistency that you need to run is something that you can capture in your model, or that you can extend your model to capture.
Right. Yeah. So in the work that I just presented, we assumed that consistency is either taken care already because the app wanted to be geo-distributed for latency, or it's a stateless app. But after this work, we have been accounting for the network and storage cost of replication, where we assume that replication is happening purely for the new geo-distribution that we introduced for availability and was not, say, happening before. So yeah, it's possible to do that, and we have formulations, but yeah, not in this time. Thank you.